And there's a lot going on in this time-lapse sequence. I feel that the spokes are trying to tell us something, although it may be days or weeks before we really understand just what they are trying to tell us. By that time, you'd all be gone, so we're going to share it with you this morning. And all of you out there can do instant science right along with the rest of us in trying to see what's happening. There's a lot of complex activity going on. One tends to see some spokes looking as though they're shearing out. Others seem to be forming. Others seem to be fading away. So why don't we just go to it, and we can all analyze the spoke problem. Go through it twice, fairly fast, and then twice a little more slowly. You have to be careful of projection effects, but it appears that some of the features actually sharpen.
There we go, coming around the racetrack. Now, briefly in front of the planet, then coming around again. Okay, now there are at least a few places where we think we see, this is going a bit too quickly, but where we think we see, right in here, instantaneously, almost instantaneously, the production of a radial spoke. There's another one right there. Wasn't there before, suddenly appears, right there, momentarily radial. That same set of pictures, incidentally, is the one that we use to look for embedded satellites in the gaps, in these clear regions, in the Cassini division in the outer edge of ring C. And the ones that Len Tyler pointed out are, in fact, the very ones that we're looking into. The ones he sees as free space, we also judge to be almost completely free of material. And it's within those regions that we're looking for these embedded satellites, which we would calculate ought to be in the vicinity of 30 kilometers in diameter. Well, a progress report on that is that Terrell has now completed 1/3 of both rings in the Cassini division and the outer edge of ring C very, very carefully, where he believes he can see anything down to 5 kilometers, certainly, and possibly a little bit smaller, and that assumes that the particle is even a little on the dark side of average for the rings, and nothing in that 1/3. Cuzzy, within the Cassini division only, has looked at the remaining 2/3 of the Cassini division, not quite as carefully. His limit is probably something of the order of 10 kilometers, but still quite a bit smaller than, the limit is quite a bit smaller than what we were looking for, a 30-kilometer satellite. Cuzzy did not find any satellite larger than 10 kilometers in either of the gaps in the Cassini division, and we now find ourselves at a point where we had hoped not to be.
It really
Dr.
is.
Smith also showed a new and spectacular color picture of the rings.
Now, this is greatly exaggerated color, but what we were concerned about were these changes within the B ring. When you look at a normal color version of the B ring, it looks fairly uniform. But when you really push and particularly get down into the ultraviolet, then we see that these are real changes across the B ring. So here's the C ring looking blue relative to the other rings. It's a little bit dark, but the Cassini looking relatively blue. And then this structure here, where this region is a little bit bluer and this is a little bit redder than average. So even within the B ring, there are differences in the spectral reflectivity. It is not a homogeneous ring in that sense.
Included in this image of Saturn are actually 4 satellites. 3 of them show up quite readily: Tethys, Dione, and Rhea. And this is the shadow of Tethys up here. But if you look very carefully, you'll see a little bright spot right here. That's Mimas, and its shadow is seen up here. This is produced in false color because it gives us a little more contrast to the features that we're looking at. The colors that go into this are ultraviolet, violet, and green, and again indicate the way Saturn might appear if our eyes were sensitive to the shorter wavelength part of the spectrum. Once again, we see this high-velocity jet, this looping feature indicative of that high-velocity jet blowing toward the east about 150 meters per second. Down below is a much weaker jet toward the west at about 15 meters per second, and then these anticyclonic features that are caught up in the shear in between. This brownish spot moving along at about something like 30 meters per second in a easterly toward the east. Note that when we look at these objects into the UV, that this brownish spot tends to have a slightly brighter center, and these two features show up quite well, and that's in contrast to the green image, black and white green image, that I'll show you in just a moment. Note the position of these two features. This is about the same latitude as this one, and so they're moving along more rapidly than this feature, which is almost standing still in between this strong jet that's moving toward the east and the weaker one that's moving toward the west. So the next black and white image now shows this region with somewhat higher resolution. This picture was taken about 2 days later. This one, in fact, on the 21st of August. And now you can just barely see those two features that showed up so well in ultraviolet.
Way. The young lady right there.
I have two questions. First for Dr. Smith. On the screen yesterday afternoon, on the limb of Saturn, I saw a lot of white flecks on the image of Saturn. Do you have any idea what those were?
Well, there are, particularly at the higher latitudes, a large number of these small white features, similar to many that we saw on Jupiter. They may be small convective elements, like a large aggregation of thunderheads or cumulus-type clouds. The resolution was probably something in the order of 100 kilometers or so that gives you an idea of the scale of those features. It's similar to what we've seen in Jupiter's atmosphere as well.